features of parent graphs. Now this one's a little bit unique, and again, I apologize because the hole punch went through my F right there. But it's a little bit unique because there is really not a true parent graph because your base can be any number. So the parent function is b to the x. Now in any given case, that b, like the first one I'm looking at, is a 2. The second one I'm looking at is a 1/2. In any case, that b can be different and is different. But it does always have to be greater than 0, because if b is a negative number, what would happen? What if you ever had, don't write this down, but what if you ever had -3 as your base to the x power? Right, every other integer that you plugged in, like on a table of values, would go back and forth between a positive number and a negative number, and a positive, depending on whether you were going to an even exponent or an odd exponent. So that would, I don't even know what your graphing calculator would do. There'd probably be something, but it's not, that is not considered. Just out of curiosity, I'm going to plug this in. -3 to the x power. Like, look at your table, right? 1, -3, 9, -27. And in the intermediate values, if x was a fraction or something, it would kind of, again, depend there. So if I look at a graph of this, we don't really see anything. Nothing comes up. That's interesting. Because I don't know that, well, it's definitely, well, is it a function? I don't know. It is a function, but it's not an exponential function. It's kind of its own beast, which I've never even studied or looked at before, so, and we're not going to now because b has to be greater than 0. But I'm kind of interested. B also cannot equal 1, for obvious reasons, right? Because then it would just be what? If it was f of x equals 1 to the x power, then it would just be a horizontal line at 1. So that can't happen. And b can't be 0 for obvious reasons, because if it was, it would just be 0, which again would be another horizontal line. Okay? So let's look at this one first. Your critical points are going to be your y-intercept, so 2 to the 0 power is 1. And that's always going to be a critical point. So down here, if I keep a tally of critical points, and the reason I'm bringing up critical points is because once we get into transformations, those are the ones we want to focus on, giving the function its general shape. So 0, 1 is a critical point of your parent function, regardless of the b value. And your next critical point, at least in this case, is when you have an x of 1. It will be 1 comma what? 2. What if your base was just b, just generally speaking? It's 1 comma what? B. Very good. Because if you plug in a 1, b to the first power is b. Okay? And we have an asymptote. Where is our asymptote on an exponential function? Jalen says x equals 0. Connor said y equals 0. Which is it? X equals 0 would be right here. And we have a point on there. So it is this horizontal line, y equals 0. And that's because this function will never become negative. You cannot get a negative output. No matter what x value you plug in, 2 to the 5th power, 2 to the 6th power, 2 to the 7th power is obviously getting larger and larger and larger. If I plug in 2 to the negative 1st power, 2 to the negative 2nd power, 2 to the negative 3rd power, we all know by now that negative exponents do not make negative numbers, right? Negative exponents make teeny tiny numbers, yes? So it'll just continue to get smaller and smaller and smaller, and as we approach negative infinity, as our x values approach negative infinity, the function approaches 0, and as we go towards positive infinity, we shoot up towards positive infinity. So your asymptote is y equals 0. And just like other asymptotes, like the asymptotes of your rational graphs, asymptotes shift with certain movements from transformations. Okay? B, similarly, has two critical points. It's got 0, 1, and it's got 1 comma b. What's our b value here? 1/2. 1 comma 1/2. And so this is going to really kind of do the opposite. Whereas we go towards positive infinity, we approach 0. But as our x values go towards negative infinity, our function goes towards positive infinity. So this one's our f of x, and this one's our g of x. I think most notably, what would you say about the difference between the f of x function and the g of x function? What would you say, Josh? Okay, good. But what vocab words? Jalen? Okay, the positive slope you would call exponential growth versus decay. So you remember that from last year. Okay? Both with the same asymptote. Any questions on that? We have 15 minutes or 1? Okay, good. On this next graph, we have exponential growth or decay. Growth. Start with your parent graph, so 0, 1, and 1 comma 3, because our b is 3 here. And this is our parent graph, asymptote, steady at y equals 0. Okay? And then transformation. So let's talk about which transformation. There's two going on here. Which one occurs first? +1, which does what to the graph? Shift left. You don't need to say horizontally because left kind of, that's a little redundant. Left is more specific about horizontal. And 1 unit. And then what does this do? Vertical reflect over x. So this shift happens first, and the vertical reflection happens second. So point by point, just taking our critical points, we're going to shift each one, left 1 unit, and then flip them. So starting with this one, left 1 unit, and then it's flipped over the x-axis. It's currently 3 above, so we're going to go 3 below. So that will be there. This point, left 1 unit, flip over the x-axis, we'll put it there. And then our asymptote, a horizontal line, shifted left 1 unit, doesn't change it, right? And then vertical reflection over the x-axis. If you are the x-axis, you're not moving. So our asymptote actually did not get affected, and our new function looks like that. Okay, so as you're adjusting and shifting and transforming these functions, take it point by point. Now, it's worth talking about right now that when I ran this sheet of paper through the copy machine, it got folded over. So this 1-5 is part of your homework. It's supposed to say on the back 1 through 76, 1s and 5s. Because I think 76 ends that section. So I just picked the sections I want you to do first, then I get the numbers. Okay, no big deal. This at the top we're going to come back to in a minute. But the next thing we're talking about is the irrational number e. Do you remember this from last year? Okay. So this is called the natural base, which we'll do a lot more of as we get into functions. Really, you guys learned last year that if we say ln of x, that means the same thing as log base e of x, correct? Okay, so that's really the context in which you learned about e the most. But this e to the x power is still an exponential function. The base is just the number e. Does that make sense? So if we were to sketch a paragraph of this, 0, 1 would still be on there. And 1 comma what? Right, 1 comma e, we'll just call it. 1 comma e and 0 comma 1. And still it's an exponential function. It's just the base is an irrational number. I mean, you could do the same thing with f of x equals pi to the x power if you wanted, right? It's just a different irrational number there. But we obviously look at e a lot because it has, you know, it is the inverse of the natural log function, which we will get to this chapter and kind of, you know, maybe learn that at a little bit of a deeper level this year. Okay? But the reason we talk about it is because when there were two formulas you had to recall last year, memorize last year. Do you remember these two? Okay. This one is compound interest that is compounding continuously. Which is really where that E is most useful. And then this one is compound interest. Really usually have a bank account, right? Where you have a certain rate and then the number of times it's compounded per year. So how do I want to say that? Compounds n times per year. So it compounds a finite number of times. Quarterly would mean 4 times a year. Monthly would mean 12 times a year. You kind of got to read into the vocab word to get your end value versus something here that's compounding continuously. Okay? So just to review, in essence, if you open a bank account, that you get 12% interest per year. If it's compounded monthly, you're getting your 12% split up into 12 parts. 1% in January, 1% in February, 1% in March. Do you remember all that? Okay? You don't remember that? Yes, no? Did she talk about this? Sounds like no. Did you know what compounding meant? Okay, yeah. So if it's, let's just hypothetically, 12% compounded monthly, you're just getting 1% 12 times. If it's done quarterly, which is what, like if you ever had, did I spell quarterly right? If you ever have like investments in the stock market, you'll get a lot of quarterly statements where you're getting 3% charged 4 times or 3% interest 4 different occasions. So in all cases, you're getting 12% total, right? But what's better? And we could go on weekly. And if it's weekly, you're getting your 12% divided into 52 parts. What's best? It seems like you're getting 12% in each case, but what's the best for you? Weekly. The more times you compound, the better for you. Okay? Because and it's probably easiest just to compare monthly and quarterly. If you do monthly, then in January you're being given your 1%, which means in February you're making interest on that interest, right? You're making 1% on your account balance, but also on the 1% that you got given to you via interest already. So you're making money off of the money that wasn't yours to begin with, right? Versus here, by the time you get to March and you make 3%, you're just getting 3%. By March here, you will have gotten the same 3%, plus you would have gotten an additional, well, by March when you get 1%, you're getting an additional 1% of what you had already earned in February and what you had already earned in March by getting those 1% added onto your balance. So we could look at actual numbers and fine-tune this and really get into the nitty-gritty detail if we had more time. But I think you get the idea if this is the second time you've seen it. On the example, we have a sum of 10,000, and this is really going to get us looking at the difference between compounding quarterly versus monthly versus continuously, and why continuous compounding is going to be the best. So the 10,000 is your principal amount, so that's the capital P for principal. Annual rate of 8%, you're going to use 0.08 as your R. Find the balance in your account after 5 years. So for part A, principal amount 10,000, 1 plus your R of 0.08 over your N is quarterly, means 4, and your exponent is 4 times 5. No, you do. Why is your exponent 20? What's that? Right, there's 20 different quarters in 5 years. So on 20 different occasions, you're going to be earning really 2% each time, because your 8% gets split up into 4 parts. So 2%, 2%, 2%, 2% on 20 different occasions, 4 times per year for 5 years. So you just type that into your calculator. There is a calculator portion on this next test. So your money will have grown to $14,859.47, which is all the motivation I need to put money in the stock market. Bank accounts aren't really going to do this anymore. Bank accounts are very pathetic. But the stock market can and will. Obviously, in the stock market, though, you can lose money, so there is a risk there. But if you're willing to wait it out and you don't need the money at any given point in time, putting it in the stock market is going to make it grow for free. And actually 8% is maybe a nice estimate for what the stock, but this year the stock market's like 20%. So imagine what something growing at 20% would do over 5 years. That would be pretty fantastic. Obviously, stock market doesn't do that. It might be 20% this year, might be 7% next year, might be 1% the next year, might be negative 2% next year. So it's, kind of a gamble, but overall it goes up and up and up if you have the time to wait it out. So invest your money is my lesson, most important of the day. Part B for monthly. We're going to split our 8% up into 12 parts, which is going to be a smaller percentage each time, but we're now going to do it 12 times 5, which is we're going to do it 60 times over the 5-year period. So your final amount in that case, if I just divide by 12 and raise it to the 60th power, I get 14,898.46 if I'm going with money, the nearest 100th. So not much more, but a little bit more, right? $38, $39 more. And then continuously is just 10,000 times E to the rate of 0.08 times 5. And you would think it would get much bigger, but actually, it gets bigger, but not by the actual growth. As you keep increasing, it's going to grow by less and less. So this just grew by $30-something. This is not going to grow by $30-something. 14,918.25. But you'll notice that, like if you do it once a year to going quarterly, it's going to be a significant difference. Quarterly to monthly is a smaller difference. Monthly to weekly will be even a smaller difference. Weekly to continuous would be even a smaller difference. But that's really the maximum that 8% will grow to, is the continuous compounding. Okay? Because, look at this. Now back to this point. no matter how many times you compound, let's say you compounded 1,000,000 times. Let's look at that function and see what happens as n approaches infinity. If I do 1 plus 1 over x to the x power, and I look at what happens as that approaches infinity, this line is tracing along a horizontal asymptote, and guess where that horizontal asymptote is? E. E. Okay, 2.7 something. If I do second trace and value and I type in 1,000 or 10,000, oh, it's not on my graph. Even if I plug in 10, this number is getting closer and closer to 2.7. Okay, so this approaches E, hence the reason why continuous compounding and infinite compounding essentially turns into the PERT formula. Did Mrs. Ziggy call it the PERT formula? Okay? That's because as this expression goes towards infinity, that value just goes towards